Hello. In this introductory lesson, I'll briefly cover the basic tools and concepts that I'll use in the rest of the lessons. Character animation often implies transformations, moving, rotating, or scaling rig elements in a scene. You can find an object's position, rotation, and scale in its attributes in the Coordinates tab. These coordinates show transformations of a specific point. It is called axis in Cinema 4D, but it is often called pivot as well. Parametric objects which have shapes described with a set of parameters, like this cube, have a pivot in the center. For non-parametric or editable objects, a pivot shouldn't necessarily be in the center, and you can move it with the Enable Axis Modification tool. I'll move the axis up now. You can see the y-coordinate of the cube has changed, although the cube has stayed in the same place. And now it rotates relative to this point as well. Each attribute that you can animate has a circle like this near it. If you click on it, you'll create a keyframe, thus saving the value of this attribute in the current frame. You can create a keyframe with a different value in the other frame, and by default, Cinema will interpolate the attribute value between the keyframes. This interpolation is displayed as a curve in the timeline in the F-curve mode. It is actually a graph that displays how the attribute changes over time. The shape of the curve is determined by the parameters of the keyframe, which will be displayed in the attribute editor if you select it. You can adjust the keyframe settings either by clicking the buttons or by modifying the tangents. You can make the parameter change linearly, that is, gradually, or you can make it slow down in the end, and so on. You can create keyframes by clicking on the Record button, and you can use these buttons to control which attributes will be recorded. You can also enable auto keyframing, and keyframes will be created automatically when you change any parameter. And I'd like to say a few words about hierarchy. This is a very important aspect of rigging, for hierarchy affects object transformations as well. Let's say this is a leg, a thigh, a shin, and a foot. These three objects are on the same level of the hierarchy now, at the root of the scene, and are not related to each other in any way. If I rotate or move the thigh, the shin and the foot will stay unchanged. If I move the foot into the shin and the shin into the thigh, they will inherit the transformations of objects higher in the hierarchy. So in this way, it is convenient to set relationships of object transformations in a scene. Objects higher in a hierarchy are called parent objects, and those lower are called child objects. That is, the thigh will be a parent for the shin, and the foot will be a child. Note that the Coordinates tab contain the object properties relative to a parent. And if I rotate the thigh, the shin coordinates will not change in any way. Cinema 4D has the Coordinate Manager, which allows you to specify world coordinates. But as you can see, you can animate only the coordinates in the object attributes. So keep in mind that object transformations are always animated relative to a parent. That is, in the parent space. If you change a hierarchy of animated objects, they may offset. For the stored coordinate values will give other transformations in space relative to a new parent. Inheriting transformations from a parent in a hierarchy is called forward kinematics, or FK. If you need to fix, say, the foot when the character sits down or walks, you'll need to offset the parent's displacement by rotating all of its children so that the foot remains in the same place. This is very difficult and inconvenient, and for such situations there's inverse kinematics, or IK. It allows you to set the position of an object at the end of a chain, while the rotations of other objects higher in hierarchy are processed automatically. Inverse kinematics is implemented as the IK tag in Cinema 4D. It is assigned to the top object in a hierarchy, to the object which an IK solver will influence. And in its settings, you need to specify objects that are lower in a hierarchy, and the external object it will follow. You also need to specify the so-called POV vector for correct processing. It sets the bending direction. You usually interact with the rig using auxiliary objects like these. They are called controllers. The inverse kinematics tag allows you to enable dynamics in Cinema 4D. Notice how the hierarchy behaves when the animation is being played. You can use this technique to create a tail and its complex movement. You can even specify a collision object to control how objects intersect with the geometry. Spline inverse kinematics is often used in rigging as well. It is implemented as a separate IK spline in Cinema 4D. This solver places objects along a spline in a hierarchy, which can be useful for customizing elastic or flexible objects. Constraints are a rather important tool for creating a rig. They allow you to connect object transformations regardless of a hierarchy. For example, with the rotation constraint, you can make an object from this hierarchy inherit the rotation of an external object. You can see that the hierarchy controls only the position of the shin, while the rotation is completely set by this object. Constraints are also implemented as tags in the object, the transformations of which will be overwritten. While in the target field, you'll need to specify the object, the transformations of which will be inherited. With a few exceptions, constraints completely overwrite the corresponding transformations. With the rotation constraint, as in this example, you won't be able to rotate the constrained object. You can create a tag from the Character Tags menu and manually configure the required parameters. Select a type, PSR in this case, and specify target. Alternatively, you can select an object for which you want to create a constraint, then a target object, and go to Character Constraints. You can also specify several targets and adjust the impact of each using the weight parameter. And of course, you can animate this parameter. Cinema 4D has a lot of constraints, but I'll cover only a few of them in this lesson. Perhaps the most commonly used constraint is the PSR constraint. PSR is short for position, scale, and rotation. So the constrained object simply inherits those transformations of the target objects. In the constraint settings, you can specify which transformations will be inherited. Moreover, you can specify different transformations for different targets. For example, one target will impact rotation, and the other will impact movement. I'll enable position inheritance for both targets. When both their weights are equal to 100, the targets will equally impact the constrained object, and the pyramid will be between them. If you decrease the weight of one of them to 0, the corresponding target will stop impacting the pyramid, and its position will completely coincide with the second target. This example demonstrates the so-called transformation blending. You can use it to combine different behaviors in one rig. Make a character's hand work in the inverse kinematics mode with the ability of switching to the forward kinematics mode when needed. The next example demonstrates the work of two constraints which are usually used together, aim and up vector. With the help of a target object, aim allows you to specify the position in space where the constrained object will be directed. It, however, doesn't control the direction in which the constrained object rotates. So the up constraint is used for the task. It creates the so-called up vector to set the rotation. It is similar to the POV vector in the inverse kinematics solver. In this case, constraints are set so that the y-axis of the pyramid is directed towards the cube, while the x-axis is directed towards the sphere. If the target of the up constraint, that is the sphere, approaches the direction vector set by the aim constraint, the pyramid's orientation will be difficult to calculate, and it may start to twist strangely. These constraints influence the rotation of the object only, so you can move it freely. A similar structure can come in handy for the eyes setup. Now I'd like to say a few words about the parent constraint. As the name suggests, it is used to simulate the inheritance of the parent's transformation. That is, the constrained object behaves as if it is a child of the target object, but it is not. The parent constraint is designed primarily for the so-called hermetic parenting, in which an object follows different targets in different moments in time. It differs from the PSR constraint mainly by its convenient interface for switching targets, and the fact that the object stays unmoved when you change the target's weight. In addition, you can still transform it. Finally, the spring constraint. It connects the constrained object to the target with a spring and reveals itself when the animation is played. It can be used to add dynamic effects to a rig, for example. A character model is usually a solid polygonal object, and its animation implies the transformations of its shape or deformations, that is, moving its points. Let's say this cylinder is a character's arm, and I want to bend it. Controlling the position of each point separately while animating will be quite difficult, for each point will have its own coordinates. So points are usually connected to the transformations of auxiliary objects. The easiest way is to create a cluster deformer. It connects points to a null and controls the influence with the help of a vertex map. You can see that the points follow the null now. You can control the strength of its influence by adjusting the vertex map tag, which I'll tell you about later. A more advanced and also the most common method of deformation via transforming intermediate objects is the use of a skin deformer. Unlike a cluster deformer, it allows you to conveniently control how the transformations of several objects influence each point of the geometry. The most convenient way to create a skin deformer is to use the bind command. To do this, you need to select the mesh, then the objects that will influence it, and apply the bind command from the character menu. It'll create a skin deformer itself and the weight tag. Also, it will automatically calculate the weights, that is, the influence intensity of each object on each point of the geometry according to the bind command settings. A list of deformers and weights is stored in the weight tag. The automatic calculation of weights doesn't always give good results, and you can adjust them by drawing on the surface with the weight tool in different modes. By default, deformer weights are displayed in different colors in the viewport for convenience. The weight tool allows you to adjust the weights of the selected object. So now I'm smoothing joint 1. You can enable the weight tool either by double-clicking on the weight tag or by selecting it from the character menu. You can also use the weight manager, which has a lot of various tools to manipulate weights. The skin deformer works in a linear mode by default, and its working principle is as follows. Each point is impacted by the parent constraint, in which all deformers with corresponding weights are specified as targets, and their transformations for a specific point will be arranged linearly depending on the weight. So artifacts may appear in the places of bending, during twisting, etc. And however you adjust the weights, you won't be able to get rid of many of such artifacts. You can change the type from linear to spherical in the skin deformer properties to maintain the volume a bit during bending, but this won't solve all problems either. Although the skin deformer has its disadvantages, there are a few alternatives to it. The skin deformer is fast enough, and it is one of the few deformation methods that real-time engines support nowadays. The objects specified in the skin deformer distribute points relative to their position at the moment of creating the skin deformer by the bind command, the so-called bind pose. You can set a new bind pose by clicking the Set Bind Pose button in the Weight tag. Joints are often used as objects for deformation in a skin deformer. This is a special type of object. They are designed to set transformations in space, like in a null, but it is convenient to create them using the joint tool. They represent a notional skeleton well and facilitate the automatic calculation of the skin deformer's weights. In general, however, any objects that can be transformed can be used in the skin deformer. Another common deformer for rigging is point morph, or simply morph, or blend shape, as it is called in other programs. It allows you to set a certain position for points and blend them, thereby adjusting the influence of each pose. You can also specify another object as a pose, thus creating the so-called dynamic morph. And if the shape of another object changes, this pose will also be updated. It is important to ensure that the number and order of points for these objects are identical, since point morph searches for a corresponding point on the target for each point by its index. And if I specify a sphere with a different number of points as a target, point morph will behave strangely. Point morph is mostly used to create face rigs. It is designed as a tag, but there is also the point morph deformer, which allows you to control the influence of the tag with the help of fall-offs or vertex maps, as well as move several point morph tags on one object. You can use point morph together with the skin deformer in order to adjust complex skinning areas. Real-time engines support it too, but it is a pretty powerful deformer in Cinema 4D, so not all its features can be recreated by an engine. You can influence the points of an object by the surface of another object using the mesh or surface deformers. In this way, it is convenient to control the shape of a high poly geometry with a simple low poly mesh. Cinema 4D has a lot of various deformers that can be useful in various situations. But I won't speak about them now, and we'll move on to the next topic. I'll tell you a little about vertex maps. Vertex maps allows you to set a scalar value or weight for each point of an object. It is implemented as a tag. If you select it, its weight will be displayed in color in the viewport. By default, red represents the weight of 0 and yellow of 100%. It is convenient to control the deformer's influence on a certain area of the surface with the help of vertex maps. For example, now the smooth deformer is smoothing the entire object equally. But if I upload the vertex map to this field in the Falloff Deformer tab, its intensity will depend on the weight of the vertex map. As you can see, when the weight is 0, the deformer doesn't work. With a double click on the tag, you'll enable the Paint tool. You can use it to manipulate the weights in various modes, either by drawing with a brush on a surface or by clicking the buttons. The tag itself is created by applying the Paint tool to an object. You can find the tool in the Character menu. Or you can use the Set Vertex Weight command, which sets the weight values for the selected points. Cinema 4D Release 20 introduced fields. This is a very powerful tool that allows you to, among other things, parametrically combine and adjust weights as layers. Vertex maps are also used for simulations to control the physical parameters of the surface and for shading. They can be used as a mask for a material, for example. Perhaps one of the most powerful tools in Cinema 4D is Xpresso Visual Programming Environment, which is available via the Xpresso tag on an object. Xpresso allows you to control almost any object attributes through various logical and mathematical operations. In the Xpresso editor, elements are represented as nodes with inputs and outputs, and you can set quite complex dependencies by connecting them into block diagrams. In this example, I've connected the y-coordinate of the sphere to the y-coordinate of the cube. So if the cube coordinate is greater than 0, the sphere will offset twice as the cube does. And if the cube's coordinate is less than 0, the sphere will remain unmoved. You can also set movements. For example, the cube rotates along a sine wave now. Cinema allows you to create user data on objects, to add attributes to control various parameters, and to use them in Xpresso, for example. I've created several attributes for this null. Boolean attributes for a sphere and a cube and a scalar radius. Then I've connected them to the enable parameters and to the sizes via Xpresso. Now, by adjusting parameters on one object, I can turn on and off the sphere and the cube and control their sizes. You can display them in the viewport to keep them at hand. Thus, you can control various parameters of the rig from one place, without the need to look for objects and their attributes each time. It is rather convenient, especially for complex structures. One of Cinema's weak spots is the need to control the order in which constraints, deformers, generators, and other objects are processed, the so-called priorities. In this example, the sphere is constrained to the cube with the parent constraint, and the pyramid is constrained to the sphere with the parent constraint as well. Now, if I rotate the cube and press cancel, the pyramid will remain unmoved for some reason. And I have to click in the viewport or click redraw to return it to its original place. And if I animate the cube and play the animation, you'll see that the pyramid is moving with a delay. This happens because Cinema 4D processes objects based on their position in the Object Manager, from top to bottom. So a dependent object should be below the object it depends on. Otherwise, there will be a delay, and the dependent objects will move with a delay. You can see that the pyramid is above the sphere and the cube on which it depends. And if you move the pyramid to the very bottom, the delay will disappear. When you can't change the position of an object in the Object Manager, for instance if it is already in the hierarchy, you can manually shift the priority of this or that element. The higher this number is, the later the corresponding element is processed. That is, I need to increase the priority value of the constraint in this example, and the pyramid can be anywhere in the Object Manager now. As you can see, the priorities are divided into several groups, which are also processed from top to bottom. Initial first, then animation, expressions, and so on. Now, I won't overload you with abstract information, and we'll better analyze specific cases in the following lessons. And this is it. I want to say that character animation and rigging especially require some technical knowledge. Some things will seem difficult at first, but you'll understand them over time. As in other areas, that is practice that makes the difference. So arm yourself with patience.